Perhaps on recent summer nights, you have felt an unusual heat, a warmth that doesn't dissipate even after the sun has set, when the air itself seems to feel thick. Or maybe you have seen those images on the news, skies turned, a ghostly orange by smoke from wildfires thousands of kilometers away, rivers running dry, and heat maps glowing with an unprecedented shade of red. These images bring a sense of unease, a feeling that something is profoundly changing. We get the sense that we are living in unprecedented times, a new and anxious chapter in the planet's history. But is that really true? If we listen very closely, not to the daily news, but to the whispers of the planet itself, we will hear an echo, a warning recorded not in ink, but in stone and fossils. A story of a past global fever, a climate catastrophe on a scale we can barely imagine. Welcome back to Science for Sleep. Tonight, we will not focus on the anxieties of the present. Instead, we will journey to a distant past, to a lost world, to learn the story of a time the Earth endured a fever far more terrible than today's, and more importantly, how life, miraculously, persisted and recovered from the ashes. This is a story of collapse, but it is also one of rebirth. Let us begin our journey to the end of the Permian period, 252 million years ago. Our journey takes us back 252 million years, to a world that would seem both alien and vaguely familiar. This is the end of the Permian period. The Earth's continents are not scattered as they are today. They are fused together into a single, colossal supercontinent called Pangaea. This immense landmass stretches from pole to pole, creating extreme climates. The vast interior of Pangaea is an arid, dry desert, a place of harsh temperatures and little rain. But along its extensive coastlines, where the single global ocean known as Panthalassa meets the land, the climate is more temperate and life flourishes. Let us imagine ourselves in one of these coastal regions, perhaps in what would one day become South Africa or Siberia. The air is different here, thicker, with significantly more oxygen than our modern atmosphere, allowing life to achieve great sizes. The forests are not made of the flowering plants and broadleaf trees we know. Instead, they are dominated by giant, primitive flora. Great tree ferns, some as tall as modern palms, create a dense canopy. Forests of Glossopteris, an extinct seed-bearing plant, stretch for thousands of kilometers, their tough, tongue-shaped leaves carpeting the ground. There are no flowers, no grasses, only the deep, silent green of a primeval world. And in this world lived the dominant land animals of the age. This is not yet the era of the dinosaurs. This is the age of the synapsids, the group that includes the ancestors of all mammals, including us. A terrifying apex predator, the Gorgonopsian, stalks these forests. It is a beast the size of a large bear, with a powerful, dog-like body and a pair of long, saber-like canine teeth, the first creature on Earth to evolve such a feature. It is a fast and efficient hunter. Its prey includes the massive, barrel-bodied Scutosaurus, a heavily armored herbivore covered in bony plates, a living tank that grazed on the tough vegetation. In the rivers and swamps, giant amphibians, some larger than crocodiles, lie in wait. Beneath the waves, the oceans are teeming with a different kind of life. Vast coral reefs, built by different organisms than those of today, create complex ecosystems. And everywhere, there are trilobites, these armored arthropodic creatures, which had survived for over 270 million years, crawl along the seafloor in their millions. The seas are also home to ancient sharks, strange coiled shell ammonites, and a dazzling variety of fish. This is a world at its peak, a stable and incredibly diverse biosphere that has been evolving for hundreds of millions of years. It is a world unaware of the cataclysm that is brewing deep within the planet's mantle. Life is complex, widespread, and seems permanent. It is a world that feels ancient and eternal, while the surface of Pangaea teemed with life in a world that felt ancient and eternal. A geological time bomb was ticking deep within the Earth. In the planet's mantle, the vast layer of hot, solid rock between the crust and the core, a colossal plume of superheated material began to rise. Imagine a bubble of immense heat, born from the boundary of the molten outer core, slowly pushing its way upwards over millions of years. It was a column of heat and pressure, a relentless force ascending through the mantle. When this mantle plume finally reached the base of the crust, in the region we now call Siberia, the consequences were catastrophic. The crust above it began to thin and stretch, like a drumskin pulled too tight, and then it broke. The first fissures opened up, not from a single conical volcano, but from vast cracks in the ground, some stretching for hundreds of kilometers. This was not an explosive eruption in the way we might imagine. This was a flood basalt event. Lava, dark and fluid, did not explode into the sky. It welled up from these fissures and poured across the land like a river of liquid fire. It was a black, viscous tide that buried entire landscapes, incinerating the great Glossopteris forests and everything else in its path, and it did not stop. This eruption continued, pulsing on and off for hundreds of thousands of years, a relentless outpouring of magma from the planet's heart. Over time, it would cover an area larger than Western Europe, with layers of basalt rock kilometers thick. The scale is almost impossible to comprehend, but the lava itself, as destructive as it was, locally, was not the true planet. The real danger, the mechanism that would trigger a global catastrophe, lay in what the magma burned through on its way to the surface. The Siberian crust was incredibly rich in vast ancient deposits of coal, oil, and natural gas, the buried remnants of the Carboniferous forests that had flourished 100 million years earlier. As the magma, at over 1,000 degrees Celsius, surged upwards through the crust, it ignited these immense fossil fuel reserves from below. It was like setting fire to the world's largest and deepest coal seam. The burning released unimaginable quantities of carbon dioxide and methane, the most potent greenhouse gases, directly into the atmosphere. The Siberian Traps were no longer just a volcanic eruption. They had become a planetary engine, pumping greenhouse gases into the sky at a catastrophic rate, far faster than the natural carbon cycle could absorb. The Earth's atmosphere, the thin, fragile blanket that had nurtured life for billions of years, was now being fundamentally and rapidly rewritten. The planet had begun to develop a fever, and the sky itself was about to become poison. The first and most immediate effect of the Siberian Traps eruption was a profound change in the sky itself. Vast clouds of sulfur dioxide, gas, and fine volcanic ash were blasted high into the stratosphere, where they were carried by global winds, wrapping the entire planet in a persistent, dirty haze. This veil initially blocked out a portion of the sunlight, leading to a brief and deceptive period of global dimming, a volcanic winter that stressed the great forests of Pangaea. But the true danger was chemical. The sulfur dioxide in the atmosphere mixed with water vapor to form clouds of sulfuric acid, and from these poisoned clouds, a corrosive rain began to fall. This was not ordinary rain. It was a drizzle with the acidity of vinegar, and it fell relentlessly upon the world for years. It burned the broad leaves of the glossopteris trees, leaving them scarred and brown. It acidified the soil, dissolving essential nutrients and making it difficult for new plants to grow. The great forests of the Permian, the foundation of the entire terrestrial ecosystem, began to wither and die under this chemical assault. But this initial cooling and the acid rain were merely the prelude to the real catastrophe, while the ash and sulfate aerosols eventually fell out of the atmosphere. The greenhouse gases, the carbon dioxide and methane released from the burning of ancient coal and gas remained, and their concentration was rising at an alarming rate. These gases began to trap the sun's heat, wrapping the Earth in an ever-thickening thermal blanket. The planet's thermostat was broken. Year by year, decade by decade, the average global temperature began to climb, rising by 5, then 8, then perhaps as much as 10 degrees Celsius. This runaway greenhouse effect transformed the climate. The vast arid deserts in the interior of Pangaea expanded, and the once temperate coastal regions were gripped by extreme and prolonged droughts. The weakened forests, already damaged by acid rain, now became tinder dry. The hot, dry conditions created a tinderbox on a continental scale. A single lightning strike could now ignite a wildfire that, fed by the dying vegetation and the hot, oxygen-rich air, could burn for months, spanning thousands of square kilometers. The sky, already hazy with volcanic aerosols, would have been perpetually filled with thick, black smoke. For the animals on the land, the world was becoming a waking nightmare. The air itself was becoming toxic, not just from the smoke, but from other volcanic gases like chlorine and fluorine. The plants they relied on for food were disappearing. The world was caught in a vicious feedback loop of heat, drought, and fire. The sky, once a source of life-giving light and water, had become an agent of destruction. But the devastation was not confined to the land. The world's single, great ocean, the Panthalassa, was about to face its own slow, suffocating, and silent apocalypse. As the skies turned to acid and the lands burned, the great Panthalassa Ocean acted as a planetary buffer, absorbing a vast amount of the excess heat and carbon dioxide from the atmosphere. But a buffer can only take so much pressure before it, too, begins to break down, and the ocean's collapse was a slow, 3-act tragedy. The first act was acidification. As enormous quantities of carbon dioxide dissolved into the seawater, it formed carbonic acid, steadily lowering the ocean's pH. For the countless marine organisms that built their homes and their bodies from calcium carbonate, the great coral-like reefs, the nautilus-like ammonites with their coiled shells, the ubiquitous trilobites in their intricate armor, and the tiny plankton that formed the very base of the oceanic food web. This was a death sentence. The very water they lived in was becoming corrosive to their existence. Their ability to precipitate minerals from the water to form their shells and skeletons was crippled. The architectural foundations of marine life began to dissolve in a slightly more acidic sea. The second act was suffocation. As the planet's fever grew, the ocean's surface waters became warmer and warmer, and warm water physically holds less dissolved oxygen than cold water. The ocean was, in a very real sense, losing its breath. At the same time, the rising global temperatures likely disrupted and shut down the great ocean conveyor belts. The massive currents that circulate water around the globe, carrying oxygen-rich surface water down into the deep. The result was the spread of vast anoxic dead zones. The deep ocean, starved of oxygen, began to suffocate. These breathless zones expanded upwards from the abyss, compressing the remaining marine life into a thin, desperate layer near the surface. A frantic competition for the last pockets of oxygenated water. The third and final act was poisoning from within. Into this warm, breathless, suffocating environment, a new form of life began to thrive. Anaerobic bacteria. These primitive organisms did not need oxygen. In fact, for many of them, oxygen was a poison. They flourished in the sulfur-rich, anoxic waters, and as they consumed the sulfur compounds, their metabolism released a toxic byproduct, hydrogen sulfide gas, a deadly poison with the characteristic smell of rotten eggs. This toxic gas saturated the dead zones, killing off most of the remaining life that had survived the heat and lack of oxygen. The proliferation of certain types of these organisms, particularly green and purple sulfur bacteria, would have turned the anoxic waters into a ghostly, foul-smelling pink or purple soup. In some models, this toxic hydrogen sulfide gas became so concentrated that it began to bubble out of the ocean and into the atmosphere, adding another layer of poison to the air and potentially damaging the fragile ozone layer, exposing any surviving land life to lethal UV radiation. The ocean, once the cradle of life on Earth, had become its tomb. It was warm, acidic, breathless, and poisoned. The intricate web of marine life, which had taken hundreds of millions of years to build, was being systematically dismantled, molecule by molecule. The great dying was now in full swing, and the final, terrible toll was about to be counted. The stage was now set for the final act of the Permian world, with a poisoned sky, burning lands, and suffocating oceans. The great, interconnected web of life began to unravel at a speed and scale never seen before or since in the history of our planet. This was the climax of the catastrophe. This was the great dying. The numbers that paleontologists have pieced together from the fossil record are difficult to comprehend. In the oceans, it is estimated that as many as 96% of all marine species were wiped out. Imagine that for a moment. For every 25 distinct species living in the sea, from the smallest plankton to the largest predators, of them vanished from existence. The most famous victims were the trilobites. For more than 270 million years, these resilient, armored arthropods had scuttled across the sea floor. They had survived multiple previous mass extinctions and adapted to countless changing environments, but they could not survive this one. The last trilobite took its final breath in the warm, acidic, oxygen-starved waters of the late Permian, and an entire, iconic class of animal was gone forever. The great coral-like reefs, which were the vibrant, bustling cities of the ancient oceans, collapsed and disappeared, leaving behind only silent, skeletal ruins. The coiled-shelled ammonites, the ancient sharks, the sea scorpions all were decimated. On land, the devastation was also immense, though slightly less total. Around 70% of all terrestrial vertebrate species disappeared. The reign of the great synapsids, the dominant land animals of the era, came to a brutal and sudden end. The terrifying gorgonopsians, with their long saber teeth, the apex predators of their world, vanished. The heavily armored, plant-eating Scutosaurus, which had browsed the Permian forests in great herds, also disappeared from the fossil record. This was a catastrophe so profound, so all-encompassing, that it is the only known mass extinction in Earth's history to have caused a significant, widespread extinction of insects, these most resilient and adaptable of creatures which had survived. Other great cataclysms were also pushed to the very brink of annihilation. In the rock layers that mark this boundary, scientists find what is known as a fungal spike, a sudden massive global proliferation of fungal spores. This is the fossilized evidence of a world of unprecedented death and decay. With the great forests gone, the land was covered in rotting wood and dead organic matter, and the fungi, the great decomposers, thrived in the aftermath. When the dust and the acid rain finally settled, and the oceans slowly began to stabilize, their chemistry over thousands of years, the world was left profoundly and eerily empty. It was a ghost of a planet, a silent and barren landscape under a hazy, hostile sky. The intricate, complex ecosystems that had taken hundreds of millions of years to evolve had been erased in the geological blink of an eye. The great experiment of Permian life was over. The question was no longer what had died, but what, if anything, could possibly survive to inherit this ruined, empty world. The great pulse of extinction had passed, leaving behind a world scoured of its former glory, a planet returned to a state of primal simplicity. But life, in its most tenacious and stubborn forms, clung on the earth was not entirely empty, but it was profoundly simplified, a pale and quiet echo of the vibrant, complex world that had come before. The great lush forests were gone, replaced by sparse thickets of the most resilient, weedy plants like hardy ferns and lycopods. The oceans, though slowly beginning to recover their chemical balance, were largely devoid of the complex ecosystems that had once defined them. The great reefs were silent, skeletal ruins. The seas were dominated by a few species of hardy shellfish and fish. The intricate web of life had been torn apart, leaving only a few frayed threads. In the aftermath of any mass extinction, paleontologists see the rise of what they call disaster taxa. These are not the largest, the fastest, or the most powerful creatures of their time. They are the generalists, the survivors, the organisms with the right set of lucky traits that allow them to endure in a hostile, low-resource environment. And in the early Triassic period, immediately following the Great Dying, one creature was the undisputed king of this empty world, the Lystrosaurus. It was not a fearsome predator or a majestic giant. It was a synapsid, a distant relative of mammals, typically about the size of a pig. It had a stout, barrel-shaped body, short, sprawling legs, and a flattened, turtle-like face with a horny beak for shearing tough vegetation. Its most prominent features were two tusks that grew down from its upper jaw. Scientists believe the incredible success of Lystrosaurus was due to a combination of fortunate adaptations. It was likely a burrower, able to dig underground to escape the worst of the searing heat and hostile atmospheric conditions on the surface. Its ribcage and lungs suggest it had a highly efficient respiratory system, which would have been a crucial advantage in the loxygen world of the early Triassic, and as a herbivore, it likely fed on the hardy roots and tubers of the resilient plants that survived, not depending on a specific type of foliage. For a period of millions of years after the extinction, the Earth was the planet of the Lystrosaurus. In some fossil beds from this time, Lystrosaurus fossils account for as many as 95% of all land vertebrates found. Imagine vast, silent, semi-arid landscapes populated only by great, wandering herds of these strange, pig-like reptiles, with very few predators to trouble them. The world was quiet. The complex chorus of the Permian forests, the buzz of countless insects, the calls of diverse amphibians and reptiles had been silenced. This was not a quick recovery. The Lystrosaurus world, this era of low biodiversity, persisted for millions of years. It would take an estimated 10 million years for the planet's ecosystems to even begin to approach the complexity they had held before the extinction. The planet was breathing again, but its breaths were shallow and slow. Life had survived, but it was a shadow of its former self. The world had become a blank canvas, waiting for millions of years of patient evolution to begin painting a new masterpiece upon it. And from the ranks of the other, much rarer survivors, the next rulers of the earth were quietly waiting for their chance. The great dying was an ending. A brutal and near-total reset of life on Earth. But every great ending in our planet's history is also a new beginning. The destruction of the old world, as complete as it was, created a vast ecological vacuum. An empty stage upon which a new cast of characters could evolve and compete for dominance. For millions of years, the world belonged to the hardy Lystrosaurus and a few other resilient generalists. But among the much rarer survivors of the Permian extinction was another group of reptiles. A group that had been minor players in the old world, living in the shadows of the great synapsids. These were the archosaurs, the ruling reptiles. Before the extinction, they were not particularly dominant, but they possessed a few key adaptations that would become tremendous advantages in the hot, dry, oxygen world of the early Triassic. Many had more efficient respiratory systems, and some were developing a more upright posture, with their legs positioned underneath their bodies rather than sprawling out to the sides. This allowed for more efficient movement and breathing. As the Earth's climate slowly stabilized and ecosystems began to reform, a great evolutionary radiation occurred. The few surviving archosaur lineages began to diversify, rapidly evolving to fill the countless empty niches left behind by the Permian fauna. One branch of this group evolved into the ancestors of modern crocodiles, becoming dominant predators in the rivers and swamps. Another branch took to the skies, becoming the pterosaurs, the first vertebrates to achieve powered flight. And a third branch, beginning as small bipedal creatures, began to grow in size and complexity. These were the dinosaurs. Their rise was not instantaneous. It was a slow, multi-million-year process of competition and adaptation. But the great dying had given them an opportunity they would never have had otherwise. It had wiped out their main competitors, the dominant synapsids, like the Gorgonopsians. With the old rulers gone, the dinosaurs were free to flourish. They evolved into a dazzling array of forms, from the colossal, long-necked sauropods, the largest land animals to ever live, to the fearsome theropods like Allosaurus and, much later, Tyrannosaurus rex. They conquered every continent, adapting to every terrestrial environment. The world that emerged from the ashes of the Permian was not a repeat of what came before. It was a new world, with new rules and new masters. The Permian-Triassic extinction event, the greatest catastrophe in the history of life, had inadvertently cleared the stage for the Mesozoic era, the age of reptiles, the age of dinosaurs. The reign of our distant mammal-like ancestors was over, and it would not return for another 150 million years, until another great extinction event would, in turn, clear the stage for them. The story of life on Earth is a story of these great cycles of destruction and creation, of loss and opportunity. The silent, empty world of the Lystrosaurus slowly gave way to a world filled with the thunderous footsteps of giants. The story of the great dying, with its toxic skies, suffocating oceans, and silent continents, can feel like a piece of ancient, distant history, a drama played out on an alien world. But the purpose of this journey into the deep past is not just to witness a planetary catastrophe. It is to hold up a mirror to our present moment. The parallels between the events of the end Permian and the challenges we face today are unsettling and impossible to ignore. The fundamental driver of the Great Dying was a massive and rapid release of greenhouse gases, primarily carbon dioxide and methane, into the atmosphere. The cause then was a colossal volcanic event burning through fossil fuel deposits. The cause today is the industrial activity of a single species, us. Though the sources are different, the geological and atmospheric consequences are eerily similar. We are now pumping carbon dioxide into the atmosphere at a rate that rivals, and some studies suggest may even exceed, the rate during the initial phase of the Siberian Traps eruption. We are, in effect, becoming a geological force in our own right. The symptoms of the Earth's ancient fever are re-emerging today. We are witnessing a steady rise in global temperatures. We are seeing an increase in the frequency and intensity of extreme weather events, from heat waves and droughts to torrential rainfall, a direct consequence of a warmer, more energetic atmosphere. Our oceans are once again acting as a great buffer, absorbing about a quarter of the carbon dioxide we release, and as a result, they are undergoing the same process of acidification that was so devastating 252 million years ago. The current rate of ocean acidification is faster than at any point in the last 300 million years, threatening modern coral reefs and the countless organisms that rely on a stable ocean chemistry. We are also seeing the spread of anoxic dead zones in the oceans as warmer waters and nutrient runoff deplete oxygen levels, and the wildfires that ravaged the dry, hot landscapes of Pangaea have their modern-day echo in the catastrophic fires now seen across the globe. Of course, the world today is different. The continents are not fused into one, and the ecosystems are more resilient in some ways. But the fundamental physics and chemistry of our planet's climate system have not changed. The story of the Great Dying, written in the stone and fossils of the past, serves as a stark and powerful warning. It shows us that the Earth's climate system is not infinitely stable. It has tipping points, thresholds beyond which rapid, cascading, and potentially irreversible changes can occur. It reminds us that the intricate web of life we depend on is fragile, and that its collapse can happen with terrifying speed on geological timescales. The past is never truly past. It is a lesson, a data point, a cautionary tale. And the story of the Permian-Triassic extinction is the most profound cautionary tale the Earth has ever written. We have journeyed back 250 million years to witness a world of fire and suffocating seas, and we have seen the stark parallels to our own time. It can be easy to feel a sense of despair in the face of such a story, but the ultimate lesson from the Great Dying is not one of inevitable doom. It is a more complex and profound story about the Earth's immense power, its deep geological rhythms, and the incredible resilience of life itself. The Earth did recover. After the fires burned out and the oceans slowly reoxygenated, life began its patient return. The process was incredibly slow, taking nearly 10 million years for biodiversity to begin to approach its former richness. But it did happen. New ecosystems emerged, new creatures evolved, and the planet was eventually repainted with a new and vibrant palette of life, leading to the age of dinosaurs. The planet has a powerful capacity for self-correction. It has feedback loops and geochemical cycles that, over immense timescales, can absorb even the most catastrophic shocks. The Earth, as a planetary system, will survive. But the story of the Great Dying is also a crucial warning about perspective. The planet's recovery operates on a geological timescale, a scale of millions of years that is almost incomprehensible. To us, the species that are lost in these great upheavals do not return. The trilobites are gone forever. The Gorgonopsians will never stalk the Earth again. The world that emerges after a mass extinction is a different world. The story, written in the stone, shows us that the Earth's climate system has tipping points. It can absorb stress for a long time, and then suddenly, rapidly, shift to a new and hostile state that can last for millennia. This is not a story about saving the planet. The planet will save itself in its own time. It is a story about preserving the specific, beautiful, and fragile version of the world that we currently inhabit, the world that has nurtured human civilization. It is a profound reminder that we are not separate from the Earth's history. We are a part of it. We are now, for the first time, the primary geological force shaping its future. And with that understanding comes a quiet, heavy responsibility. The past does not offer easy answers, but it offers wisdom, a deep context for our own moment in time. And perhaps, by understanding the story of the Earth's greatest fever, we can learn to better navigate our own.